So, N2O nitrous oxide for all practical purposes is O. So, wherever you have N2O, you can as well treat that as simply O, because you know all nitrogens want to become N2, what else? Then we will be applying all these very shortly after I complete 15-16 points. We will apply them into reactions, and that will be the actual important point, application of these things. Li plus Na plus etc. What do you get under this etc.? All the first group: lithium, sodium, potassium, rubidium, cesium, francium, and starting magnesium, magnesium 2 plus, calcium 2 plus, all those in the second group. Perhaps ClO4 minus, PO4 3 minus. These are all spectators. Spectators, they have no reactivity whatsoever. They don't react at all. What is the reaction? When somebody is not happy in his state, suppose N2O is not happy to be N2O, it wants to become N2. But these fellows are some of the happy people. They don't do anything, they have no reactivity. Suppose if I write NaClO4, what do you see here? You have to tell me, sir, I don't see anything there. Why? Na plus is a spectator, it doesn't do anything. ClO4 minus, it doesn't do anything. Both are spectators. Therefore, they are as good as not there. They are spectators. They have no reactivity. So, suppose if I am talking about LiAlH4, here lithium has no kind of, so it is a spectator, forget him. It is just AlH4 minus, that is the reactant. The reducing agent which reduces carbonyl compounds and others. What is important is AlH4 minus, Li plus is least important. We have NaBH4, NaBH4, in which Na plus BH4 minus. Now, Na plus once again is a spectator. The 11th reactivity. All reactions of silver nitrate precipitation only. What do you mean by that? Silver nitrate, it doesn't have any special type of reactivity. It only precipitates others. For example, suppose you have a solution of sodium chloride. Sodium chloride solution. In a solution, you know the salt will be in ionic form, Na plus Cl minus. The moment you add silver nitrate solution to that, what will happen? You are adding silver ions and nitrate ions. These two will precipitate. Silver chloride gets precipitated. You get AgCl. So, it is not just silver chloride. Suppose you have sodium bromide, same thing. Sodium bromide, sodium iodide, phosphate, silver carbonate, anything, almost anything. But fluoride, hydroxide, and of course nitrate, there are few compounds of silver that are soluble. Let us see who they are. Ag2O, silver oxide, AgOH, silver hydroxide, AgF, silver fluoride, AgNO3 and Ag2S2O3. These are the only soluble substances. These are the only soluble substances of silver. Only soluble substances of silver. Listen, don't see them as 5 compounds. Don't see them as 5 compounds, because what is an oxide, what is a hydroxide? Same, oxide in water, silver oxide in water is nothing but silver hydroxide. So, Ag2O, AgOH, AgF. So, oxide, hydroxide, fluoride almost one and the same. So, these 3 are not 3 different compounds. So, suppose there is a fluoride already present. When you add silver nitrate, silver fluoride doesn't precipitate, it is fairly soluble. So, silver thiosulfate. Therefore, except these 5, suppose you have, you see, NaCl, I don't need to express once again in the form of a question. NaCl plus AgNO3. What will you get? What is complete the reaction? Here silver chloride gets precipitated, and of course NaNO3 doesn't get precipitated. NaNO3 remain the way they are. So it's not just chloride. So that's what I mean to say. NaCl, NaBr, NaI, Na2CO3, sodium carbonate, sodium phosphate. So anything, phosphate, sulfate, chromate, dichromate, permanganate, whatever that is, all of them are insoluble. But you know, if suppose you have a fluoride here, fluoride, oxide, hydroxide, and once again nitrate, thiosulfate. Except these 5, all other reactions precipitation. So you roughly have some 15 compounds, chloride, 15 other anions. You have chloride, bromide, iodide, sulfide, carbonate, phosphate, all of them are insoluble. So just except these 5 anions, you may have many anions and all of them are insoluble. All reactions of AgNO3. Instead of expressing this as a question, look here. NaI reacts with AgNO3 to give a precipitate of A, sodium silver hydroxide, or silver oxide doesn't come. NaNO3, it doesn't precipitate. Silver iodide, that is the precipitate. So why should we take a question and 4 options? Instead of giving a question, if you learn a concept, you are learning 20 questions, 20 such questions. Isn't it a waste of time and waste of paper? AgI and Ag2CO3. How can you get a carbonate? That can never happen. So AgI. So you have many reactions. NaI, NaBr, same. So that's why I said all reactions. Suppose there are 25 anions, except with 5 anions, with all others it's a precipitate. So I can generalize except. These are the only soluble substances. Now, non-metals, concentrated nitric acid. So for each reactivity, you have an average of 10 reactions. Suppose if I teach you 20 principles, you will be able to answer 200 questions. So instead of learning them in the form of a question, you learn the underlying principle from which you can yourself make many questions. Non-metals, concentrated nitric acid. What do you get? Oxy acid of maximum oxidation state. For example, if you take carbon, you get H2CO3. So, for example, you take phosphorus, what is the maximum oxidation state? Oxy acid, H3PO4, phosphoric acid. So, once again we are preparing oxyacids. If you ask me how are oxyacids prepared, if you remember well, by adding carbon dioxide to water, non-metal oxide to water, you get them. By hydrolyzing the halides, PCl5 on hydrolysis gives this. So, we have already seen 2 methods, oxide plus water, halide plus water, non-metal plus concentrated nitric acid. Of course, you may require small heating also. So, sulfur will give H2SO4, even chlorine goes to HClO4. But remember, iodine, you get HiO3. It is rather surprising. Maybe surprising to you, it's not surprising to me. How come? Iodine, HiO3. Why are others going to their maximum state? +7, +6, +5, +4. Why are they going to their highest state? They want to make use of maximum number of bonds to get rid of their lone pairs. Here, iodine still has a lone pair. 1 iodine, 2 double bond O and 1 OH. So, there is a lone pair. But iodine is not afraid of lone pairs. Small atoms are only afraid of lone pairs. Here, iodine being a big atom, it's not afraid of lone pairs. So, here you are. So, it's not just here. You see on many other occasions, iodine, I said non-metals want to go to maximum oxidation state. It seems iodine is not that of a non-metal, not a great non-metal. It has some metallic properties also. It has a metallic cluster. It is a solid metallic cluster, grey violet solid, shining, and iodine most of the time prefers to be in I2 state rather than in any reactive state. Therefore, we can conclude that iodine many areas. So, it is not behaving like other non-metals who are afraid of lone pairs and run for a maximum oxidation state. They want to make use of all their electrons, but not the case with iodine. 13. Cn minus, Br minus, I minus, they are first reducing agents. First reducing agents, then only ligands. Listen to me. They first reduce others. What do you mean by reducing agent? They all give electrons. So, I minus prefers to be in I2 state. Cn minus, SCn minus, NCS minus, all permutations, combinations that arise out of this CNS minus, all those things, and N3 minus azide ion, all these are called pseudo halides. Why are they called pseudo halides? Strictly speaking, they are not halogens, but they consider themselves as halogens. Cn minus will tell you, sir, I also form HCN, sir. I also form HCN, hydrocyanic acid, a monobasic acid, like Cl minus forms HCl, and Cl minus exists as diatomic. I will also exist as Cn twice. Cyanogen, they even have taken the name gen there, halogens, cyanogen, thiocyanogen, isothiocyanogen. And you definitely know azide N3 minus wants to become N2 because all nitrogens want to become once again diatomic. HN3, it forms hydrazoic acid, HN3, hydrazoic acid, in which nitrogen of course is minus 1 by 3, and it exists diatomic N2. What else? So, N3 minus. So, these are all called pseudo halides. Why are they called pseudo halides? In matter of factly, they are not halogens. They don't form part of the C. Halogens, that name comes, halogens come from, they form a part of the C. In fact, they are responsible for the C, but these are not present in the C. If cyanide is present in the C, all of us will die. They are called pseudo halides. And Cn minus, look here, look at its behavior. Why does it behave as a reducing agent? You will be seeing Cn minus would rather prefer to lose the electron and want to form a bond with another carbon. I long since told you all carbons want to form a bond with carbon. Electropositive elements, they want to combine with electronegative elements. Positive, the first group sodium wants to combine with the seventh group chlorine. Electropositive elements want to combine with electronegative elements, but carbon, which is at the center of the periodic table, it is neither electronegative nor electropositive. Metals want to combine with non-metals, non-metals want to combine with metals, but carbon is neither highly metallic nor highly non-metallic. Therefore, carbon prefers to form a bond with another carbon, which is called catenation. The property is called catenation, long chain compounds. So once again, Cn minus exists as cyanogen, carbon-carbon rather than HCN. So, first they reduce others, they give electrons. What do you mean by reducing agent? Every moment you should recollect that, without that there is no chemistry. Cn minus is a reducing agent, means Cn minus gives electrons to others. Now, who can convert to F minus to F2? No one can do that. I already told you it's next to impossible. It's a very difficult task. Why? Fluorine always wants to be in its F minus state rather than combining with another fluorine. I told you two fluorines hate each other because of the too many lone pairs in too little space. So, F minus F2, F minus doesn't give electrons to anybody, means F minus is never acts as a reducing agent. That is the meaning. If I say F minus never acts as a reducing agent, the sense is not carried completely. So, what to be said? 2 F minus F2. Who can convert F minus to F2? No one can do that. No one indeed can do that. Then 2Cl minus 2Cl2. Who can do that? 2Cl minus 2Cl2. Who can do that? 2Cl minus 2Cl2. Very few people. F2 can do that. O2 can do that. K MnO4 among others can do that. MnO2. Only 4 people. Even dichromate cannot do that. Means removing electrons from chlorine minus is also a very difficult task, because chlorine holds electrons very firmly. You can't remove very easily. If I am holding something loosely like this, perhaps you can remove. But if I am holding like this, perhaps not easy. So, strongly held electrons, since they are highly electronegative, they keep electrons very close to themselves. But Br minus to Br2, who can convert Br minus to Br2? Many people. There are many people in line. I perhaps cannot give the list. Many. To I minus to I2, everyone. Everyone. Anyone who is interested in removing electrons. So, anyone interested in electrons can take my electrons, because I minus itself is ready to lose electrons. I minus volunteers electrons. Please take my electrons. Please take my electrons. Everyone. So, everyone means everyone who is interested in taking electrons. If you are not interested, you won't take. Okay. It's like a free to air channel. If you are interested, you can watch. It's not a pay channel for which you need not pay. Pay channel you have to pay I minus I2 free. Free for all. But Br minus, many people can still watch. And Cl minus to Cl2, very few people it is private. F minus F2, no one. Highly kept like that. So, if you understand this, we can answer more questions. We will be applying these principles. What all you need to do is take a principle and apply that in 10-15 cases, no less than 10-15 cases. And whenever you look at a reaction, you try to find the reactivity. And I am giving you the ultimate reaction. Listen. Before that, let me give you something. I think it is a 17th point. Unexpected solubility. It may be the 16th or 17th, it doesn't matter. Unexpected solubility is due to complex formation. What is this? This word perhaps will not carry a total sense. Like unexpected means you will not be able to explain easily. Why is this happening? You still are in doubt. Whenever you are in doubt, you perhaps have to use this. For example, AlF3 is not soluble in water. It is not soluble in water, but soluble in NaF solution. NaF solution. Why? What do you get in NaF solution that is not present in water? Water you have H2O, NaF, what do you have? Don't tell me, sir, we have Na plus. I already told you Na plus is a spectator. F minus. What is the role of minus in a group? I long since told you, that was my first statement perhaps. What is the role of F minus? Any minus donates. And who is aluminium? Any question on molecules of beryllium, boron, aluminium, I taught you. Any question on molecules of beryllium, boron, aluminium, think in terms of electron deficiency. If you have forgotten, there is nothing I can do about that. But I gave you very few principles. I didn't teach you many principles. Very few principles to understand chemistry. These are all tools to understand. So, it appears very strange to you. Why is this happening? AlF3 is not soluble in water, but soluble in NaF. How can I remember all this? You need not remember anything. You just think about it. Apply your brain. What is there in sodium fluoride solution that is not present in pure water? F minus. Here you have H2O. Here also you have H2O, F minus, Na plus. So, Na plus is as good as not there. It is a spectator. Na plus has no role in anything. So, it is F minus that is responsible for whatever is happening. How is F minus responsible? F minus donates a pair of electrons to aluminium and it forms a complex. And the complex is called Na3AlF6. Suppose the molecule AlF3 becomes AlF6 minus it's ionic. AlF6 3 minus, in fact, AlF6 3 minus. So this is sodium ion, AlF6 ion. Ion itself means soluble. Complexes, complex ion. Therefore, there are hundreds of questions. AgCl is not soluble in water. Silver chloride, we already saw. None of the compounds of silver are soluble in water. AgCl is not soluble in water, but soluble in ammonia. Why? What is there in ammonia which is not there in water? Ammonia can form a complex with silver, silver amine complex. Like that, anything, any question you have to see like that. AgCl is not soluble in water, but soluble in KCN, because cyano complex, dicyanoargentate 1, which we saw in the extraction of silver in metallurgy. So you should not look there, that is a separate topic and this is a separate topic. You integrate all of them, add 2 and 2 and get to the conclusion. Okay. Now, unexpected solubility is due to complex formation. The 18th point. So, ferrous sulfate solution. Solution, I repeat, because if I don't mention the physical state, if I say ferrous sulfate is added to permanganate, the first doubt you must get is what state you are mixing. Suppose if I take a salt of ferrous sulfate and a solid of potassium permanganate, what happens when two solids are mixed? You at best can get a mixture. So that's of no significance. FeSO4 solution plus KMnO4 solution. FeSO4 solution plus KMnO4 solution and a pinch of acid. Listen, before you add the acid, you just add ferrous sulfate and permanganate. Nothing will happen. You are adding two solutions in which you have ferrous ions, in which you have sulfate ions, in which you have K plus ions, in which you have permanganate ions. I told you potassium ions are spectator and sulfate ions are spectators most of the time. I cannot generalize that sulfate is always a spectator, but definitely I can tell you most of the time it is a spectator. Or sulfate, sulfur in plus 6 state, K plus is a spectator, MnO4 minus plus 7. These two are in their maximum oxidation state, they can't do anything to each other. Both are in maximum oxidation state, one cannot bring the other down, both are at a height. Only those who are here can bring you down. Okay, so since both are in max, so sulfate at least in this reaction you must realize is a spectator. Sulfate, sulfur is in maximum oxidation plus 6. What can it do? Nothing. Okay, this also maximum. So both are, so to say, oxidizing agents, therefore they can't do anything to each other. So only a reducing agent can do something. So before you add acid, look here, just ferrous sulfate solution, permanganate solution, what will happen? Nothing will happen. You don't see anything. Ferrous sulfate is light green in color, permanganate is purple in color. What will happen? Nothing. But the moment you add H plus, my God, H plus means acid. What you get is a brown residue, rust at the bottom, a precipitate brown, and this color is decolorized. So what you see the moment you add acid is a colorless solution in which some brown precipitate is there. What has happened? H plus, H plus. What is the role of H plus here? So let us eliminate the spectators who don't do anything. Ferrous plus permanganate, Mn double bond O, double bond O, double bond O, O minus. Got it. Who is ferrous? I already discussed. Who is ferrous? Try to recollect. Ferrous wants to become ferric. It's a spectator ready to give electrons. So ferrous is ready to give electrons for all intents and purposes. But who is ready to take? Ferrous says, permanganate, manganese, you want electrons? Manganese says, me electrons? I am giving electrons to 7. I am giving 7 electrons to these oxygens. I am giving electrons myself. Who are you to give me electrons? Get lost. Oxygen, do you want electrons? Oxygen say, are you mad? Manganese is already giving me electrons. Why should I take electrons from you? So nothing will happen. ferrous is ready to give electrons, but no takers. Like if I call another chemistry faculty and say, sir, come here, I will teach you chemistry, what will he say? Idiot, who are you to teach me chemistry? I myself teach. So here manganese is actually giving electrons. Oxygen, who wants electrons, is already getting electrons. So ferrous, though ready to give electrons, no takers. So it's a very difficult thing here. What will happen? The moment you add H plus, the moment you add H plus, that is acid, oh my God, H plus. What happens is a miracle. These oxygens, 4 oxygens, will run like mad. They'll come out immediately. They say, manganese, thank you. We're going. Oxygens say, thank you, manganese, thank you. Why thank you for? Thank you for your hospitality. All these days you have given us electrons. Thanks for that. But why are you going? Children, why are you going? Manganese, if we stay with you, you have only give us electrons. You only give us electrons. It is like, okay, you're giving electrons. So what happens when you go out? You see, I get electrons from Mr. Ferrous and protons from that acid. Double benefit. If we stay with you, what are you offering? You are just offering electrons. If we are with you, if you are in your house, you are serving us only electrons. But the moment we go outside, we get electrons from ferrous and protons from the acid. What will you do with them, boys? What will you do with them? Sir, you don't know. We combine the electron and the proton, we get a hydrogen atom and we can become H2O, which is our life's dream. That is our goal. We want to become H2O, don't you know? All oxygen atoms want to become H2O. So we are going out to become H2O. So all these 4 oxygens will run away, leaving manganese behind, 4H2O. That is the stoichiometric reaction. This is stoichiometry. This is redox. All oxygens want to become given a chance. I told you, what is the chance oxygens are expecting? For oxygens, electrons is no big business. Anyone can give electrons to oxygen, or oxygens can take electrons from virtually anyone. They are good at that. But if oxygen gets electrons and protons, it's a different ball game altogether. Because oxygens will become H2O and that is a dream come true for them. So, H plus. So, listen to me. So, this is the underlying principle of chemistry. When I say chemistry, your level chemistry, I am not interested in what you don't need at your level. Okay, whatever is required at least up to the JEE advanced level is this only. Beyond this, there are so many things which you can perhaps learn immediately the day after your advanced is over. But until then, don't be interested in unnecessary things now. H2O. All oxygens want to become H2O. So, oxygen, if somebody gives him hydrogen atoms, he will be very happy to take. Very happy to take. Suppose you give me a sandwich, I will be too happy to take that. But someone is offering me a bread and someone is offering me those vegetables. Nobody is, so what will I do? I take the bread from them and the vegetables from them, combine, make a sandwich out of themselves and eat it. Actually need to eat a sandwich. But what you are giving me is plain bread and someone they are giving me some salad. So I combine them and make a sandwich out of themselves. So I would have preferred to have hydrogen atoms. But since I am not getting hydrogen atoms just from one source, I am collecting electrons from one source, protons from the other and combining them to get hydrogen atoms. You listen, if you want hydrogen atoms, what you need to do is, suppose here is a permanganate, potassium permanganate, and you take somebody called substance that can give hydrogen atoms. Suppose you take hydrogen and you heat it. Okay, when you heat this hydrogen molecules. These molecules will break into atoms, and that atoms can be used by oxygen. But see, you are talking about heating. I don't know how much amount of heat might be required to break the manganese oxygen bond. So, what are you talking about is a violent reaction in which heat is involved, but the reaction in front of you is a silent reaction, mind you. How come? You don't know what's happening. You just combined a salt and another salt, water, acid. Everything happened silently. Those who want to give electrons, they gave. Those who want to give acids, they want to give protons. Acid means one who gives a proton. Who else? So, we can get hydrogen atoms. But to get hydrogen atoms, you have to heat a substance. Here, this is a silent natural reaction. I told you, a reaction in which a heat is involved is an unnatural reaction, obviously. Unnatural reaction. Then, FeSO4. So, listen. So, ferrous, permanganate, H plus, what will happen? Ferrous, permanganate, H plus acid. Ferrous wants to become ferric, permanganate wants to become Mn2 plus, permanganate. Okay, I forgot to tell you why permanganate becomes Mn2 plus. Look here, for manganese, plus 7 and plus 2 are preferred states. Of course, plus 4 is in fact a better state, but for the time being, let us confine to plus 7, plus 2. So, manganese prefers to be either in plus 7 state or plus 2 state. Chromium, plus 6 or plus 3. Okay, plus 6 or plus 3. These are the preferred states. There can be other oxidation states also, but I will say as far as this lecture is concerned, you can say plus 7, plus 2 are preferred, plus 6, plus 3 are preferred. So, ferrous wants to become ferric, permanganate wants to become manganese 2, and so what will happen? You get H2O. How many? All 4 oxygens ran out to become H2O. 8H plus, 4H2O, 8H plus. Okay. So, why do you require 8H plus? Each oxygen requires 2 protons and of course 2 electrons. I repeat, oxygen doesn't want electrons and protons. Oxygen indeed wants hydrogen atoms. Oxygen indeed wants hydrogen atoms, but since it is not getting hydrogen atoms directly, it is collecting electrons from one source, protons from the other. Electrons, protons. Now, ferrous wants to become ferric. Now, manganese plus 7 to plus 2. So, you must have remembered when oxygens are going out saying goodbye manganese, what will manganese say? Okay, boys, you are going out, you want electrons and protons also. Since I am unable to give you protons, you are going in search of protons, I agree, but I myself is a metal. I myself am a metal. I want to lose electrons, you know. So, take 2 of my electrons also, 2 of my electrons also. It is not just ferrous that wants to be in plus 2 state or plus 3 state. I am also a metal. I never want to be in 0 oxidation state. I never want to be in my elementary state. We are metals. We always want to lose electrons, 1 or 2 electrons. But 7 electrons, if you want to run away with 7 electrons, perhaps I cannot give you 7 electrons permanently. What do you mean by giving 7 electrons permanently? Becoming a manganese 7 plus ion. A manganese 7 plus ion, which is not what do you call manganese 7 plus ion, is it's not that important. So, plus 7 plus 2, 8. So, ferrous wants to become ferric, permanganate wants to become Mn2 plus and 4H2O. So, since manganese is giving 2 electrons, MnO4 minus, this electron also comes from potassium, K plus MnO4 minus, this electron. So, these 4 oxygens indeed require 8 protons and 8 electrons, only then you get 4H2O. So, we have 4 oxygen atoms from permanganate, 8 protons. Okay, if you want 16 protons also I am ready to give. You take an acid, that can give 8 protons, for which you may have to take 4 H2SO4, 4 H2SO4. Perhaps HCl is not the right bet for this reaction, HCl, because Cl minus also acts as a reducing agent. So, perhaps we take H2SO4, non-controversial H2SO4, which gives you 4 H2SO4, 4 H2SO4 to make 8 protons. So, the question is, where do you get the 8 electrons from? I tell you, you already got 1 electron from potassium, K plus 1, and manganese, even after the reaction is over. What do you mean by reaction is over? Even when oxygens are leaving its home, oxygens are going out, walking out of manganese house. They are walking out, but even then manganese gives 2 electrons. Losing 7 electrons permanently may be difficult, but losing 1 or 2 electrons is not a big deal for metals. Sodium easily loses 1 electron, magnesium 2, even aluminum 3. So, losing 1, 2, 3 electrons is not very difficult. Permanently, losing permanently, forming an ionic bond. But losing 7 electrons permanently perhaps is difficult. Therefore, manganese offers only 2 electrons in a pack. Take 2 electrons and go. So, Mn2 plus. So, how many more electrons are required? Plus 1 plus 2. So, 3 more electrons, 5 more electrons are required. 1 from potassium, 2 from manganese. So, what do you mean by Mn2 plus? Manganese has given 2 electrons even after the reaction. So, you require 5 more electrons, for which you just write 5 ferrous, which will become 5 ferric. So, how else you will find this? Plus 7 plus 2 plus 7 plus 2, the difference is 5, you write the 5 here. Plus 2 plus 3, the difference is 1, you write 1 here. This is quite a mechanical process. Perhaps you cannot explain why are you doing that, but right now you have an explanation, haven't you? So, don't do it mechanically. Why 5? Why 5? What is the role of ferrous? You may find this to be ferrous. For me, it is not ferrous. I see only an electron there. What I am seeing is 5 electrons. I am not seeing 5 ferrous ions. Ferrous ion is not my friend. I have no business with ferrous ion. Chemistry, I have business with only electrons and protons, those who give electrons and those who give protons. 5 electrons. Yeah, 5 ferrous means 5. A pack of 5 electrons, 2 electrons, 1, 8. So, oxygens have collected 8 electrons from 8 different sources and converted themselves to. So, this is the balancing of a redox reaction consciously, not mechanically. Plus 7, plus 2, 5, write the 5 there. Why 5? Why are you seeing the difference? So, what we cannot explain in stoichiometry, we can explain only through the help of this inorganic understanding. What is the reason? All oxygens want to become H2. And you will be surprised, this is, oxygen finds it to be very, very easy in organic. You know what? In an organic reaction, CH3CH2OH, you know all oxygens want to become H2O. This oxygen also want to become H2O. It already has got 1 H, needs just 1 more H, hydrogen atom. Hydrogen atoms, they are not readily available. If they are not readily available, what will this fellow do? If you heat that with HI, red phosphorus HI is a very strong reducing agent. Red phosphorus plus HI at 250 degrees centigrade. Okay, you are freely giving me hydrogen atoms. So, if you are giving me hydrogen atoms, I will be very glad to take. H2O is easily formed. But if you do not want to talk about heating, so what all will oxygen will ask you is, sir, give me 1 proton please. Just 1 proton. Just 1 proton. Yes, 1 proton. Sir, how will you manage with the proton? Sir, don't worry, I already have the electron. Where from? Sir, any moment I can just grab the electrons from carbon, the helpless carbon. What can carbon do? Nothing. So, you just add a proton. 1 proton can cause all the damage. 1 proton, what will oxygen say? Carbon. Okay, I am going, taking your electron also. Carbon has no say. Carbon has to be submissive. Okay, sir. So, H2O. The so-called protonation, the so-called H2O being better leaving group. Why is H2O a leaving group? Why is H2O a leaving group? Because all oxygens want to become H2O. When oxygen becomes H2O, it doesn't want anything else. It will retire. Once you get what you want, you should be happy. You should be happy, and if oxygen is too happy. So, what happens next is history, you know, plus, and of course, one more hydrogen will go, a double bond is formed. But the underlying principle of both organic and inorganic is all oxygens want to become H2O. In organic compounds, oxygens will just ask you for protons. Permanganate, if these oxygens want to go out, they have to look for electrons from one source and protons from one source, because manganese will not gift back electrons for oxygens. Maybe it can give 1 or 2, but it can't offer all the 8 required by or all the 7 required by these oxygens. So, in inorganic chemistry, you have to search for electrons and protons. You have to look for electrons also. But in an organic compound, oxygens easily get whatever the number of electrons they want. That is no big deal.